All right, students, in today's session, we are going to discuss a situation. So, I'm talking about a situation, not a concept. The concepts that we will be using to study the situation, I believe you are all aware of those concepts. If you are preparing for NSEP or even for JEE, then you are aware of those concepts. I'm going to discuss a specific situation which is generally not covered when the teachers teach you for JEE or for NSEP in classrooms. Okay, but there are many questions on this situation. Okay, so what is this situation? Let me first tell you about that. So the situation that I am talking about would be force on a moving charge particle in a uniform magnetic field. Now till this everything is okay. You have studied this. In a viscous medium. Okay, now this is something which is new, probably. Okay, we are going to discuss the force on a moving charge particle in a magnetic field, in a uniform magnetic field, in a viscous medium. Okay, now let me first demonstrate that the situation that I am discussing here is not a a one-off situation. There are many questions on this which are present in standard text, standard books, and to prove that point, I will first show you some questions that I've picked from Pathfinder, a very popular book. Okay, so I'll demonstrate some questions from Pathfinder. Okay, and maybe you can pause the screen and you can then attempt those questions first to see whether you can solve these questions without my help or not. Okay, later I will demonstrate, I will show you the answer of those questions as well in this video itself. Okay, so after you have attempted those questions, you can check whether you are getting the right answer or not, and then I will explain the theory that you need to attack those questions, and we'll see that how it becomes very easy if you are aware of that theory to attempt all these questions. Okay, so let me start with showing you the question. So I'll move out of the frame, okay, so that you can pause the screen and you can attempt these questions if you want to do that. Okay, all right, so that is one thing. Next question, see, this is again a Pathfinder question. The details of the question are written on the screen, so you can check it from there. Okay, next we'll go to the third question. Okay, so again I'm staying out of the screen so that uh, yeah, okay, you can notice, and then we go to the next question. This is actually a comprehension. Question number 13 to 15 are covered through this. Okay, then we go to this. Okay, and finally this is the last question, and now let me demonstrate the answers of these questions to you. So guys, so the answer to the first question would be this. Okay, the answer to the next question would be this. Okay, and then the answer to the third question is this, and then the answer of the comprehension are this. So what was my reason to demonstrate these questions, to show these questions here? First, the topic that I'm going to cover, it attacks many questions which is present in a book such as Pathfinder, a very standard book, a great book. Okay, let's see the theory that we need. Okay, so guys, what are the prerequisites? Okay, so like what are those concepts that I think you should be knowing to understand this situation? Okay, so what are the prerequisites? Okay, so the first one, okay, you should be aware of force on a moving charge particle, magnetic force on a moving charge particle. So we write that force as Q into V cross B. So I'm pretty sure that you are aware of that. Okay. Secondly, we should be aware of how to write the viscous force. So more often than not, the viscous force is written as to be directly proportional to the velocity and opposite to the velocity. The power is usually 1. There are situations in which the power is something else from 1, and this B is a proportionality constant. So this is how we write magnetic force. This is how we write the viscous force. Okay. So these two things I think are the basics that you need. Apart from that, the usual things that we like the force balance and writing F equal to ma and those things you will need. So these are the two basic things that you need to know. Okay, now let me start. Okay, let me start. So what is the situation? Okay, so keep paying attention, everyone. Okay, so we have a coordinate axis. Okay, let's say this is y-axis, let's say this is x-axis. Okay, now what we did, suppose we projected a particle. Okay, we projected a particle of charge q and mass m. Consider the charge to be positive. Okay, and let's say we projected it with a velocity u at an angle theta naught, like this. Okay, we projected it, and let's say that there is viscous medium present here, like the particle is being projected in a viscous medium, ignore gravity, and let's say there is a magnetic field also. So magnetic field is along negative k direction. So we are writing magnetic field as minus b naught k cap. So magnetic field is inward. Okay, so we can draw crosses all over the screen indicating that the magnetic field line is going inward. Now we want to analyze the motion of the particle, like at a general time t, we want to know where the particle would be, how with which. Okay, and again there is a viscous medium, and the force of viscosity will be written by this. So these are given to us. So now we want to know the displacement vector, the velocity vector as a function of time. If we know the displacement vector, we can talk about the coordinates of the particle. Okay, that will simply be the x displacement and the y displacement in this particular situation. We will also talk about the distance covered by the particle. Okay, so we begin our discussion from here. Okay, we know what is given to us. We know what we want to find out. Okay, I'll write it also, like what is our aim. Okay, what do we aim to find? Okay, so our aim is to find, okay, we wish to find velocity vector as a function of time. If I'm saying that I'm aware of velocity vector as a function of time, it basically means that I'm aware of the x component as well as the y component. I'm also aware of the speed of the particle as a function of time. Okay, that is one thing. I would like to know, let's say, the displacement vector. Again, if I'm aware of displacement vector, I'm aware of many other things. I would like to know the distance covered by the particle. So these three are our focus areas. Okay, now let's start the discussion. So first thing, are we expecting the particle to continue to move on this straight line? What do you think, guys? Okay, like let's start from absolute basics. So the first question that I'm going to ask myself is, am I expecting the particle to travel on a straight line with a constant velocity? That means without reducing the speed? Probably no. Okay, first of all, there is a viscous force which will act opposite to the velocity, and this will lead to a loss of kinetic energy. It will do negative work, and remember, magnetic force cannot do any work. So there are two forces, magnetic force and viscous force. Out of the two forces, one cannot do work and the other will always do a negative work. So the kinetic energy is bound to decrease. So the speed will definitely decrease. So one thing is for sure, that the speed is not going to remain the same. It will decrease. Okay, so my question was, will it move in a straight line with a constant velocity? No, the speed is definitely decreasing, so we can't say that the velocity is constant. Now let's focus about the direction. Like, are we expecting it to travel on a straight line like this? Well, magnetic field is inward, velocity is in this direction, charge is positive, so it will experience a force perpendicular to its velocity. So yeah, it will not continue on a straight line, it will deviate. Okay, it will deviate, and not only that, the magnetic force will be continuously acting on the particle. So to begin with, I can think of that in this particular situation, the particle is expected to go on a curved path like this, something like this. Okay, now what happens subsequently is something to be seen. Okay, but this is what I can think of. So what we will say that, okay, let's say after a general time t, the particle is somewhere here, the velocity is, let's say, v, it is making an angle of phi with the x-axis. Okay, so this is the situation. Okay, now in this situation, if I talk about the forces on the particle, okay, if I talk about the forces on the particle, let me draw forces with red color. So there would be a tangential force which is b into v. I am depicting the direction, so I am only writing the magnitude now. And there would be a force in this direction which would be qvb. Okay, so magnetic force, and this will be perpendicular to the velocity. So I have written the magnetic force, I have written the viscous force. Okay, this figure is quite small. Let me copy this figure on the next slide in a larger dimension. Okay, so that we are able to understand things. So I'll do the same thing. This was our trajectory that we drew. Okay, and we depicted velocity with a blue colored arrow. I think it was blue colored arrow only. So we depicted velocity like this. Okay, this was a line parallel to x-axis. This angle was phi. And as far as the forces were concerned, we depicted one force in this direction, which was BV. We depicted one force in this direction, which was QVB. Okay, now let me draw some lines parallel to x-axis and parallel to y-axis, and I would like to draw them in a light color. Okay, this seems pretty light. So this is x-axis, this is y-axis. If this angle is phi, this angle will also be phi. This is 90 minus phi, this phi, and then this angle will also be phi. Okay, so this is the situation. We have drawn all the forces on the particle. There are two forces, magnetic force and viscous force. We have drawn them both. Now what I'm going to do, the first thing that I'm planning to do is I'm planning to write force equation, that is Newton's second law, F equal to ma, in tangential direction. Let's see what does it give us. Okay, so we are planning to write, first thing that we are doing is we are writing F equal to ma in tangential direction. Okay, that means parallel to velocity. So let's see what it will give us. Okay, so the force parallel to velocity is 0, opposite to velocity is BV. So 0 minus BV is the force in the direction of velocity. So it should be equal to m into dV by dt, or we can also write it as m into v dV by dl, where L is the distance covered or length along the trajectory. Okay, remember acceleration can be written as dV by dt or v dV by ds, where ds is the small displacement. Okay, in case of small displacement, that is as good as distance covered. So this is my equation number 1. Okay, I'll use it when I need it. So my plan is to first write down all the equation, and then we will start doing the manipulation to solve those equations. Okay, right. So this is my equation number 1. Now my next concept that I'm going to use would be writing. Okay, I will write F equal to ma in normal direction. Okay, so what is the force in the normal direction? The force in the normal direction is QVB. Okay, so the equation that we get, QVB is equals to m. Now, how do we write the normal acceleration? The normal acceleration can be written as v into d phi by dt, the rate of change at which the velocity vector rotates. Okay, so we can write it like this. Okay, so this becomes our second equation. Now, what was the color? Okay, I was using green color to write the equation. This time I use blue color. Okay, so this is my equation number 2. Okay, this is my equation number 2. I'm going to use it later on. Okay, okay. Next, I'm going to write force equation in x direction. Okay, so next is F equal to ma along x direction. Okay, so let me go back to the figure. So in this direction, I don't see any force. The x component of QVB and the x component of BV, they're both along negative x direction. So BV cos theta. Okay, BV cos theta. Okay, so the equation that we will be getting, that equation will be BV cos phi, actually not theta, with a minus sign. Okay, and QVB sin phi it would be. This is equals to m into acceleration in x direction, that can be written as Vx into dVx by dx, or if you want, you can also write it as mx into dVx by dt. Actually, mx is not there. It's only m. Okay, now there is another important thing to note, minus v cos phi. What is v cos phi? Let me go back. What is v cos phi? This is v cos phi is Vx, and v sin phi is Vy, the y component of velocity. Okay, so this will become BVx plus QBVy is equals to m into Ax. Now, what we are going to use in place of Ax is something that we can decide later. So all of this is our equation number 3. Like whichever version you want to use, you can use, but this forms equation number 3. And now let us write a fourth equation. You might have guessed it already. I'm going to write it in the y direction. Okay. So we will next write F equal to MA in y direction. Okay, we are going to write F equal to MA in y direction. So how do we write it? Let me go back to the figure. Okay, so in y direction we will have QVB cos phi and BV sin phi. Okay, so we will write QVB cos phi minus BV sin phi is equals to MAY. Okay, and again V cos phi, so that will become Vx, and V sin phi will become Vy is equals to MAY. So this is our fourth equation. So we have got 4 equations, and now we are going to start solving them. Okay, so let's see how to solve them. Okay. Okay, so start from equation 1. Okay, so what was equation number 1? Let me go back. What was equation number 1? Okay, equation number 1 was minus BV into M dV by dt. Okay, so let's see. Okay, so it was minus BV into M dV by dt. Right, now this will become minus B dt is equals to M dV by V. Okay, now you can integrate on both sides. So if I integrate here, the limit of time will go from 0 to t. The limit of speed will go from u to v. Okay, u to v. So minus b into t is equals to m into ln v by u. Okay, and now if you rearrange it, you will get v is equals to u times of e raised to power minus bt by m. So from this, this is the first equation that we can learn, that speed is equals to u times of e raised to power minus bt by m. So the speed is continuously decreasing. Okay, after infinite time, the speed will become 0. So from here, we also know that the particle will come to rest after a long duration, after a very long time. Okay, now that was one way of solving. That was one, like we'll obtain results now. So this is my, let me write it as R1. So this is my result 1 that I'm going to remember. My result 2 will be again starting from equation 1, the other version. Okay, starting from equation 1. Okay, so equation 1 was minus BV is equals to M. We wrote V dV by dL. So this V and this V gets cancelled, and what do we get? We get minus B dL is equals to M dV. You integrate on both sides. L changes from 0 to L. V changes from U to V. So we can write minus B into L. L is the distance covered, okay, is equals to M into V minus U. Okay, or the distance covered can be written as M by B into U minus V. So this is the formula for distance covered in terms of speed. Okay, so this is result 2 to remember. Okay, the same can be written like this. We can write L is equals to M by B into U minus U e raised to power minus BT by M. Okay, or in other words, you can write MU by B into 1 minus e raised to power minus BT by M. Okay, so this is your next result to remember, distance covered in terms of time. Okay, having said that, if you remember result 1 and result 2, then result 3 is not needed. You can instantly write result 3 using result 1 and 2. So what we did, essentially we just replaced V from equation 1. So therefore If you remember 1 and 2, then 3 is redundant. You can readily use it. Okay. Now that is, so three equations we have already written. What else can we do? So my third solving strategy would be to start from equation 3. Okay, starting from equation 3, let's see what we get. Or not from 3 actually, starting from equation 2. Let me go back and check. The equation in which we wrote along the normal, I think that was equation 2 only. So along normal we got QVB is equals to MV d phi by dt. So we'll start from here. Okay, so what do we write? We write QVB is equals to MV d phi by dt. Okay, now this V gets cancelled. So QB dt is equals to M d phi, or QBT. You know, when you integrate from 0 to t, phi changes from theta naught to a general value. So QBT is equals to M into phi minus theta naught, or in other words, phi, okay, is equals to theta naught plus QB by M into T. Now remember that when a charged particle moves in a magnetic field, magnetic field which is perpendicular to initial velocity, the outcome is circular motion with an angular velocity of QB by M. I can see the same thing here. So let me write this result as theta naught plus omega t, which is so familiar and which is so easy to remember. Okay, what we are choosing to do here is that we are representing omega as QB by M. Okay, so this would be my, so basically the velocity vector is rotating with a constant omega. It is rotating with a constant omega, which is QB by M. Okay, so this would be my result 4. Okay, this would be my result 4. Okay, now to get further result, lot of solving needs to be done. Okay, so next we are going to write like our step 4. Okay, step 4 would be to simultaneously solve the equation that we got from third and fourth way. So yeah, equation number 3 and equation number 4, we plan to solve them simultaneously. Okay, so I'll have to come back and check what the equation is. Okay, so my strategy is to simultaneously solve equation 3 and 4. Okay, so yeah guys, the derivation is getting a bit lengthy, but that's okay. Okay, so equation 3 I'm rewriting. Okay, equation 3 I'm rewriting. I'll have to go back and check the equation. Okay, so it is, minus is there, BVX plus QBVY. Okay, BVX, I hope we remember that. Okay, BVX, minus is there, BVX plus QBVY is equals to M into X. Okay, so that is dVX by dt. Now what you can notice from here is this, minus B by M, Vx can be written as dx by dt plus omega, this M comes down, QB by M is omega, into dy by dt is equals to M dvx by dt. So dt gets cancelled from everywhere. Okay, so this equation can now be integrated, all the terms are integrable. Okay, so we end up with B by M into delta x. Okay, and because starting position was origin, so delta x is only x actually now. But let me keep on writing delta x. Omega delta y, okay, is equals to M delta Vx. Okay, now this is not any final version of the result that we want to remember, but this is one of the versions. Okay, now let's call it as equation number 5. Okay, we will do a similar step by using equation number 4. Okay, we'll do a similar thing by using equation number 4. So equation 4 was, we can probably recall it by looking at this. It should be QBVX. Okay, what I remember is it was QBVX minus BVY is equals to M dVy by dt. We'll go back and confirm this. So QBVX minus BVY. Okay. QBVX minus BVY. So we are okay. Okay. Now what can we do here? We can again write this as QB dx by dt minus B dy by dt is equals to M dVy by dt, and again you can check that this gets cancelled, this gets cancelled, this gets cancelled, and now everything is integrable. So when you do the integration, you end up getting QB delta x minus B delta y is equals to M delta Vy. So this is your equation number 6. Now in equation number 6 and in equation number 5, okay, we can say that delta x and delta y are the two unknown quantities and other quantities are known to us. Okay, other quantities are known to us. Why are we saying that delta Vx is known to us? Because we calculated the speed after a specific time and we calculated phi after a specific time. So if we know the speed, if we know the phi, then we can readily write delta like the x component of the velocity and the y component of the velocity. So delta Vx and delta Vy is something that is known to us. So delta x and delta y are the two unknowns. We want to solve these equations. So we'll solve them simultaneously. Okay. So my next step of calculation would be solve 5 and 6 simultaneously. Okay, my next step would be to solve. Okay, so how do I do that? I will first write those equations and then only I can start solving. So let me first write those equations. So if I write equation number 5, it is minus B by M delta x plus omega delta y is equals to M delta Vx. I hope this was the equation. Yeah. And the other equation is, okay, the other equation is omega delta x minus B by M delta y is equals to M delta Vy. Again, let me go back and check. QB delta x, so that is, we divide the entire equation, we'll get omega delta x, divide the entire equation by M minus B by M delta y is equals to delta Vy. Okay. So the M is not there, sorry. This M won't be there. Okay. Now to solve them simultaneously, what do? I multiply this entire thing. So I see that delta x, the coefficient of delta x is negative here, it is positive here. I try to cancel them out. So I'll multiply this entire equation with omega and I'll multiply this entire equation with B by M. Okay, and then I plan to add them. So when we do that, the coefficient of delta x will be B by M into omega. Here it will be omega into B by M. So this is going to get cancelled. This is negative, this is positive, they will be cancelling. Now this is negative, this is also negative, they will get added up. Okay, so we will write minus delta y into, this will become omega square and then B by M square. So omega square, okay, plus B square by M square is equals to, on this side we get omega delta Vx. Okay, so omega delta Vx plus B by M delta Vy. So that's it, we obtained the value of delta y. Let me write it here. Okay. So delta y would be omega delta Vx plus B by M delta Vy divided by omega square plus B square by M square. Okay, with a negative sign actually. This is minus delta y. Okay, so there is a negative sign too. So this is delta y. Similarly, to get delta x, you can either substitute this value in any one of these equations, or alternatively, you can try to eliminate delta y from these equations. So you will multiply this with b by m, you will multiply this with omega, and then you will take the difference. Okay, I think that way it would be easier for me. So let me do that. Okay, so I'll now try to solve for delta x, and to do that I will multiply with this b by m. Okay, so when I multiply it with b by m, I get minus b square by m square delta x. Okay, so this term becomes minus b square by m square delta x. Delta y is going to get cancelled. Here we will get omega delta vx. So let me write here omega, not omega. We were multiplying with b by m, not omega. Okay, so b by m delta vx. Okay, b by m delta vx, and here we were multiplying with omega, so we will get omega square, but we were taking difference now. We were taking difference, so minus omega square delta x, and here it is again omega delta vy, but there will be a negative sign, so minus omega delta vy. So from here we obtain delta x as, I'll adjust the minus sign here, I'll make it as omega delta y minus b by m delta vx divided by omega square plus b square by m square. Okay, so we obtained delta x, here we have obtained delta y. Let me write delta y again here. So delta y would be, so there is a negative sign, okay, there is a negative sign, so minus, and then omega delta x plus b square by m square delta, this is delta vy, not y. Okay, so omega delta this is also delta vx. Now we are in a position to write displacement vector. We got delta x, we got delta y, so we are in a position to write displacement vector. Okay, like how will we write it? The displacement vector will be delta x I cap plus delta y j cap. You have both. Now if we were to find distance from the origin, okay, if we were to find distance from the origin, okay, let me give some names to this, we need to remember them. So the last name that we gave to remember was R4, okay, R4, right, this was R2, okay, R1, R2, R3, R4. The next thing that we want to remember is this. So this is R5, and now we are trying to get R6. Okay, so mod of S, okay, this would be root of delta x square plus delta y square. Now one thing that we can see is that the denominator will be omega square plus b square by m square. And now what else will be in the numerator? We can go back and check. So this square plus this square. Okay, so this square will become omega square delta vy square. Okay, where we'll get minus 2 times omega b by m this, and here we'll get plus 2 times, so that term will be cancelled. Omega square delta y, okay. So what we will be getting here is omega square delta vy square plus delta vx square, okay, and plus b by m square and delta vx square plus delta vy square. This is what we will get. You can try it out. So from this, what does it become? It becomes root of delta Vx square plus delta Vy square divided by root of omega square plus b square by m square. So please remember this result also. Okay. Now we have obtained everything that we wanted to know, and we can now jump to solve questions. So our result 7, okay, that was result 5. So this is result 6 in that case. So students, remembering these 6 results will enable you to solve all the questions that are displayed at the beginning of the session. Now you may be thinking that it was a long and painful derivation, but if you start doing it yourself, you will find that it may be long, but it is not very painful. The equations that we wrote were simply force equations, F equal to ma in 4 different directions, and then we just manipulated those equations. So it is not that difficult. Okay, and if you remember these results, then you will be able to solve all the questions. Let's start. So guys, one thing, I will need these equations, I will need these equations, and as of now, maybe some I remember. Okay, so I'll just see if I know the equations. Okay. Okay. All right, guys. So what you can do before you start attending the question, all the results that I have asked you to learn, okay, R1, R2, R3, R4, R5, R6, write them on a piece of paper and then continue with the session so that you can apply them in the questions. Okay, when we need to apply them in the question, you are able to do that. Okay, so this is the first question. Okay, let's see. So this question says, in a region of space, a uniform magnetic field of induction minus Bk is established. A particle is moving with a velocity v in this region, experiences a viscous drag. Okay, a particle of mass and charge q is projected with a velocity u in this region. Find its displacement when it practically stops. Okay, so dear students, see, same situation that we have discussed. The only difference is that we have projected it along the x-axis. So in this question, what is happening is that this is x-axis. Let's say this is y-axis. Okay. Now the particle, okay, the particle has been projected along x-axis with a speed u. Otherwise, everything is same as what we used for our derivation. Like the magnetic field is along the k direction. Okay, and things like this. So what will happen? The equations that we have derived, it indicates that the velocity will decrease continuously. So the particle will stop after infinite time, theoretically infinite time. Delta phi, okay, like the rate at which the velocity vector was rotating was constant. Okay, like the equation of phi, that was constant. So the velocity vector is rotating with a constant rate and it is slowing down. Okay, so when you think about these two things, you conclude that the particle should probably move like this. So, and then it should come stop. So the question is asking us, this distance. See, the question says, find its displacement when it practically stops. So we did write a formula for delta x and delta y that will directly give us the displacement. So our formula for delta x, okay, or okay, in this situation, in this situation, if I ask you the value of delta Vx, okay, change in the x component of velocity, will you say it is 0 minus u, and therefore, because the final velocity in x direction is 0, the initial velocity in x direction is u, so this is delta Vx, okay. What about delta Vy? So initial y component was 0, final y component was 0, so this is 0, okay, this is 0. Otherwise, everything is same. Now, if you substitute these values in expression for delta x, okay, so what was our delta x? Okay, what was our delta x? So instead of going back on the slide, I have written it here. So delta x was omega delta y minus b by m delta vx divided by omega square plus b by m square. So here what does it become? Delta y, so this is delta vy actually, not y, delta vy. So delta vy is 0. So minus b by m into minus u divided by omega, that is q b by m square plus b square by m square. So that is delta x. Okay. Now what is delta y? Now the expression that we derived for delta y, okay, that was minus of omega delta vx, okay, plus B by M delta Vy, and then omega square plus B by M square. So minus omega minus U plus 0 divided by QB by M square plus B square by M square is what we are getting. That's it, guys. You can now check. So the denominator, we know what will it be. The x component would be plus bu by m, and again this m square can go in the numerator. So if I further simplify it a bit, okay, I can see that it can be simplified a little bit more. So it will become mbu upon qb square plus b square, and similarly this will become what? Again m square will go into the numerator, so it will become m square omega is qb by m, so qb by m 1m will get cancelled, okay, so qb by m 1m got cancelled, into u divided by qb square plus b square. So this thing into I cap plus this thing into j cap, that should be the answer. The denominator we know, numerator is mbu I cap and mb, okay, mubq. Let's see. So here b is k. In this question, b is same as k. So mbu and qbmu. Okay, so you got the answer. So you see that if you have derived the result, if you remember the result, this question was solved very, very easily. Okay, now if we go to the next question. Okay, this question says a particle of mass m and charge q is projected with a velocity v naught in a viscous medium where a uniform and a constant magnetic field of induction B exists everywhere in a direction perpendicular to the direction of the velocity or projection of the particle. Okay. Okay, the force of viscous drag is given by, okay, find the distance traveled by the particle during a time interval from the instant of projection until the velocity vector turns. So here we have to find out the distance covered. Okay, we have to find out the distance covered in a period when the velocity vector turns by an angle of 2 pi radian. So we have written phi as theta naught plus omega t. Okay, so when it turns by an angle of 2 pi, it means the angular displacement. That means phi minus theta will become equal to omega t, and this value is 2 pi. Okay, so the time that we are talking about is 2 pi by omega, or you can say it is 2 pi m by qb. Now in this time, what is the distance covered? That is what we want to know, and we did write a relationship between distance covered and time. Okay, what was that relationship? The relationship was that distance covered is m into u into b, and then 1 minus e raised to power minus b by m into t. Just put the value of t here and you got the answer. So m u by b, 1 minus e raised to power minus b by m into 2 pi m by qb. M gets cancelled. So finally the answer is, in this question u is given as v naught. So m v naught by b, and then 1 minus e raised to power minus 2 pi small b by q capital B. This should be the answer to this question. So we are actually solving the question pretty fast now. Don't you think, guys? We got the answer. We are solving the question at a rapid rate now. Okay, now question number 16. Okay, this question says a ball of mass 1 gram and a charge 2 microcoulomb, okay, is falling vertically with a terminal velocity of 0.1. All right. Okay, in a viscous fluid after a uniform and constant. This is actually a good question, guys. Okay, I mean the previous two were also good, but after the things that we derived, the previous two questions became very easy. This one will still be difficult even after the derivations that we have done. Okay, so let's see. Okay, after a uniform and a constant horizontal magnetic field of induction B is switched on, it is observed that the ball acquires another terminal velocity. Okay, and power dissipated in the viscous medium becomes half times of the power dissipated prior to switching to the magnetic field. At what maximum value of magnetic induction is this possible? Now, at what maximum value of magnetic induction? So, all right, okay, we are seeking some kind of maxima. Dependence of the viscous force on the velocity. So, we can't assume that viscous force is directly proportional to the speed. We cannot assume that. The question has denied that. Okay. So let me explain the question to you first. So the question tells us that there was a particle, okay, which was falling. The mass of the particle is given to us, the charge is given to us, and even the speed is given to us with which it is falling. Let me check. So mass is 1 gram, charge is 2 microcoulomb, and speed is zero point 0.1. Okay, so 1 and 2 microcoulomb. Okay, so mass is 1 gram, that is 10 raised to power minus 3 kg. Okay, and then charge, okay, that is 2 microcoulomb, and the speed with which it is falling was 0.1 meter per second. Okay, it was 0.1 meter per second. Okay, so let me write the speed as u. Okay, now when this particle is falling, the question says that it is falling with terminal velocity, which means that the net force on the particle should be 0. And what are the forces acting on the particle right now? The forces that would be acting would be a viscous force, and we don't know how to write it. Like I should assume it to be what? To be dependent on what power of v? I don't know that. Apart from that, the other force would be the force of gravity. Okay, mg. Okay, there is no other force, there is no magnetic field right now. Now why are we talking about gravity? Is there anything that can vertically, the moment you see the word vertically or horizontally in a question, these words make sense only when gravity is involved. Okay, so what is vertical direction? That is the direction along gravity. What is horizontal direction? That is the direction perpendicular to gravity. So if the question uses the word vertically, horizontally, it means that you have to consider gravitation. Okay, all right, now as of now we can write mg is equals to viscous force and the rate at which power is dissipated. Okay, so power is dissipated like the same rate at which work is being done. Okay, so this is minus mg. You are, if I am talking about the magnitude, okay, the rate at which power is dissipated, that is mgu. The rate at which gravitational energy is being lost, okay, so that is the rate at which power is dissipated. Okay, right, now we switch on a magnetic field and we see that another terminal velocity is achieved. Now my first question is this another terminal velocity, is it going to be vertical? It cannot be vertical. That's a very important idea in this question. That's a very important key idea. If there are students who are trying this question by assuming that the next terminal velocity is also vertical, then you are doing something which is fundamentally incorrect. Like you can argue and you can prove that it cannot be vertical. Because if it is vertical, think about this. If it is falling vertically, the viscous force has to be opposite to velocity. So viscous force will be vertical, mg will be vertical, and magnetic force will be horizontal. Now if there are no horizontal forces, who will balance magnetic force? And if nothing balances magnetic force, how can we say that the terminal velocity has been achieved? Because in terminal velocity the acceleration has to be 0. So if I assume this to be falling vertically, I arrive at a conclusion that the net force is still not 0 and therefore terminal velocity cannot be achieved. Okay, so what I should do is this. I will say that I don't know that in which direction the particle is falling. Okay, maybe it's falling by making an angle with the vertical. Okay, so maybe this is vertical direction and possibly the particle is traveling like this, it's, so maybe this is the speed, the new terminal speed, let's call it as v. Now the forces acting on the particle would be, there would be a viscous force which will be different from the previous one. Let me write it as Fv prime. Okay, the mg force will still be same, there will be no change in the mg force. Okay, yes or no everyone? This is one thing. Okay, now just in case someone is wondering, sir, you did not consider the buoyant force here. If you think about this, I mean, you're right. I forgot to consider buoyant force. That's absolutely correct. Having said this, probably it will not matter. I'm not sure. But what I'm going to do, I'm going to say that, okay, let me treat this mg force as resultant of mg and buoyant force, because in this situation also mg is downward, buoyant force is upward. Okay, so this can be treated as mg effective. Let me treat it as mg effective. And here also buoyant force will be upward. Let me treat it as mg effective. Okay. If I'm falling short of information, then I'm going to consider it as mg, and I'm going to assume that we were not supposed to consider the buoyant force because nothing was mentioned regarding the densities. Okay, densities of liquid on the object. I hope it is not mentioned. Yeah, it is not mentioned. Okay, so when I consider mg as mg effective, I have technically taken care of the buoyant force. Okay, now I'm not sure how much this angle is. Let this angle be theta. And now the magnetic force, okay, the magnetic force has to be somewhere here. It has to be perpendicular to the velocity. Okay, so it would be QVB. Okay, it has to be, and why not in this direction, sir? Because if it is in this direction, then the three forces will not add up to give a 0. Now the three forces can add up to give me a 0. Okay, so what are the equations that I'm going to write? So first thing, I'm going to make use of the information given to me. What information am I talking about? So the question tells me that the power dissipated in the next case is half of the power dissipated in the previous case. So uh, half of the power dissipated. Okay, so yeah, of the power switching to the prior to the, okay. So now the power dissipated would be written as like mg effective cos theta into v. So we will write mg effective. It's ultimately the power of the gravity which is getting dissipated. So mg cos theta into v. Okay, this is the power dissipated, and this is half times of the previous power. The previous power was mg effective into u. So you see that this gets cancelled. Okay, this gets cancelled, and we are left with cos theta into v is equals to 0.1 into 1, 0.5. So that is 0.5 into 1. Got it? Okay, or if we want, we can just write it in terms of u also. Okay, we can write it in terms of u also. So I can write 0.5, or you can write it as eta into u. If you want to keep everything in terms of symbols, let us keep everything in terms of symbols. So this is what we have got. Okay. Now let me write this as equation number 1. Okay. Now I'll go back, and what I'm going to do, we got v cos theta, right? So if I draw a horizontal line here, this angle will be theta. Okay, this angle will be theta. Okay, I'm trying to choose this direction so that, no, this direction so that FV prime doesn't come into play. So the component of mg effective here would be mg effective sine theta. Okay, let me go here. So mg effective sine theta. mg effective sine theta. Okay, mg effective sine theta is equals to QVB. Is equals to QVB. Okay. This is what we are getting. Okay. And we got a relationship. So V can be replaced here. So we will get mg effective sine theta is equals to Q into V. V is eta u by cos theta into B. From here we will obtain B as mg effective sine theta cos theta, mg effective sine theta cos theta by eta u q. And if you multiply and divide with 2, then 2 sine theta cos theta becomes sine 2 theta. Okay, so next step we can write it as m into g effective sine 2 theta by 2 times of eta u q. Now you see that B is a function of theta, and we are looking for the maximum possible value of B. Okay, so this value maximum can become 1, and that will happen when theta is 45 degree. So from here we can declare that B max. Okay, B max is how much? B max will correspond to the situation when sine 2 theta becomes 1. So it is mg effective by 2 eta u q. Now, because mg effective is present in the answer, I am now saying that the buoyant force is not given, like we have not been given enough information to talk about buoyant force. I'll ignore the buoyant force, and therefore my answer will be this. Okay, so let's check what the answer is. mg by 2q eta. So yes, the buoyant force was indeed ignored. Okay, the buoyant force was ignored. Okay, now this is the comprehension, guys. Okay, after doing all these questions, I'm pretty sure that you should be able to do this comprehension on your own. It is a decent enough question. Like, it is not very easy, but at the same time it is not very difficult also. You apply the equations that we have derived and you will be able to solve this comprehension. So I'm leaving this question as a teaser to you guys. Okay, I hope you attempt it. I hope you get benefited from this session and you follow this session. Okay, and guys, if you like the session, if you, of course, unlike the other YouTube session that you see, this session was completely focused on academics, which I usually try to do. Okay, so if you liked it, please hit the like button, subscribe our channel if you haven't done that already, and do share it with your friends, guys. If you enjoyed this session, do share it with your friend. Tell them what you liked about this session, or tell them why watching this session is going to help them. Okay, and that will give us a lot of encouragement, and that will motivate us to continue bringing such sessions for you. On that note, I'll say bye-bye to you guys. I'll show the answer to these questions again. Okay, where is the answer? Okay, so here the answers are CAD. So attempt these questions, everyone, and bye-bye for now. I hope you enjoyed this session. Bye.